I'm actually a little bit nervous, so I'll get the nervousness out of the way. Yes. Take the nervousness away from you and put it in. So it's my great pleasure to introduce Michael Machala, who will be defending his PhD thesis in material science and engineering today. I thought I would take a trip back a little bit more than 5 years ago when I first met Michael. I remember we sat in the second floor office, the small conference room in Machala, and we discussed, what we can do. You told me you're interested in sustainability, research in that area. You're also interested in fundamental material science. You're interested in how this could be applied to technology. And I thought, oh, I have the perfect project for you. I'll take only about a year or two. We'll move on to something really interesting after that. Being the excellent salesperson I am, I thought, yeah, this will be, really great. And you start here, you go there, and then all will be finished, and we'll do much more. It turns out that I underestimated how complex a project like this can be. Michael had the desire to really link fundamental science at the very basic level to the technology. This is not something that's easy to do, because you really have to understand something and then turn around and engineer something useful out of it. I think this is a rare achievement in material science and engineering. This is why we have science and engineering in MSc. On a more personal note, this is always a great day for advisors to be able to introduce, because we're very advising for a defense exam. It's also a very special one for me because Michael is one of the first students I have in the group, is in the first class of students at Stanford. Those who are teachers would know that first class holds a special place in an advisor and a teacher's heart. I think over the years, I have made a lot of mistakes. Michael has tolerated them. And I just want to say thank you to Michael, because I also learned a lot from you. But most importantly, this is your defense, so please tell us more about what you have learned in the past 5 years. And without further ado, Michael.
Back 5 years again, initially, and I'm going to start off with a poem that I wrote the day that I decided to join Will's group, November of 2011. I walked your knee to an open field where I scanned every degree, to find the landmark worthy of the quest to search to see, spotting 3 familiar shapes and starting straight away. With gradual slope and familiar scope, I felt secure and stay. What often happens as we go, content with comfort came, a scent, I think, an unknown sound that tracks from whence it came. I stopped and pondered, weighed and wondered, points from A to Z. Pivot, climb to mountaintop, what dangers lie ahead? I pivot, dig toes in the earth and seek the unknown hill. The eyes will ache and heart is quick, but eyes are eager still. And the name of that mountain is Engineering Actions. Now, this mountain is actually called Dalgiri. It is the 7th highest in the world. And like all mountains and most of the Earth's crust, it's composed of oxide materials. So today I'm going to talk to you about how we can put a certain class of oxide materials to work to generate and store energy more efficiently. What is also found in the Earth's crust are fossil fuels. Now, among the cleanest is natural gas. And you can get energy out of natural gas using a turbine engine. Now, turbine engines are intrinsically inefficient because you must convert the energy stored in the fuel to heat, then to mechanical energy, then to electrical. So you have a lot of inefficiencies. This turbine engine is at the 500 megawatt level. And when you want to scale it down to smaller, the inefficiencies decrease. Fuel cells are intrinsically more efficient. They convert energy stored in fuel directly to electricity. And when you scale them down from megawatts to kilowatts, they don't lose their efficiency. So you can imagine them being right next to your house. So let's take a look at the efficiencies. A good, very large turbine engine is about 40% efficient. A lot of the energy lost is lost as heat. You can recover some of this heat and generate electricity. And the current world record for this turbine engine shown here is 62%. Now, if we go over to fuel cells, like I said, they're more efficient. Here we have about 60%, and that is increasing. And this is for solid oxide fuel cells, which is the class that I work with today. Further, you can regain some of the heat lost here, and you can drive the efficiency up even higher. So to put efficiency into context, at the 1 gigawatt level, A 1% increase saves about $5 million in fuel per year, and also saves a lot of CO2 emissions, which is something we need in our modern day. Now, in addition to CO2 emissions, combustion is a pretty chaotic process. It's very hot, and it has a lot of side products, such as nitrous oxides, carbon monoxide, and sulfoxides. Now, because fuel cells are a much more controlled reaction, you produce orders of magnitude less than what you do with the combustion process. So it kind of sounds too good to be true right now, and it kind of is. Fuel cells are about an order of magnitude more expensive than natural gas turbines per installed kilowatt. And this is because they operate at high temperatures, here about 800 degrees Celsius. And it's very expensive to create these modules so that they can operate at such high temperature. If you drive down the temperature, you can use more inexpensive materials. And this can reduce the cost significantly. But with reducing the temperature comes a host of problems that I'm going to talk to you about today. But before we get into those, I haven't told you what a fuel cell is yet, so let's get there. So if you open up one of those modules, you have a stack of fuel cells. And one stack looks kind of like this. Now, a schematic, to simplify, is shown up here. We have three important components. We have the cathode on top, which interfaces with oxygen. We have the solid electrolyte. An electrolyte is something that conducts only ions. In this case, it conducts only oxygen ions. Okay? And at the bottom, we have the anode. That interfaces with the fuel. So the way this happens is you have oxygen on the cathode side reacting with the cathode. It then has to incorporate into the material itself and travels through the electrolyte. And then finally, it travels into the anode where it can react with the fuel, shown here as hydrogen. It has a lot of energy stored inside it. And what it produces is water. Now, for this to actually happen, these materials must also not only conduct ions, but it also conduct electrons. Not the solid electrolyte, that's only ions. If the solid electrolyte conducted electrons, you would just get electrons going straight through and you couldn't get anything out. You couldn't get any useful energy. So what you can do is if you separate the process, you can actually use the high energy electrons on the fuel side going through a circuit, say a light bulb, and you can use that energy to do something useful. Now, if you run the reaction in reverse, and you say you put energy in, say, from the sunlight, you can run the reaction and create fuel directly, say, splitting water into hydrogen. But today I'm going to use the example of a fuel cell. And as you lower the temperature, kind of the rate-limiting reaction happens at the cathode. It's how does oxygen gas get into the cathode itself? Now, we have to talk about the cathode a little bit. So, the kind of benchmark catalysts for oxygen transformation reactions, such as the one I just mentioned, are these precious metals here, such as platinum and iridium. Perovskite oxides make a much larger percentage of the periodic table. So this is kind of a material scientist's dream. You can choose materials, elements that are much more abundant and less expensive than those platinum precious metal catalysts. And so, now that I've told you what a perovskite oxide has in it, what does it look like? So here is a unit cell of the perovskite oxide structure. It has the AbO3 unit cell. We have the A site cations on the four corners, or 8 corners rather. We have a B site cation, traditionally a transition metal in the middle, with a 3+ positive charge. And then on the faces of the cube, we have oxygen anions. And then in total, we have 6 positive charges on the cation side and 6 negative charges on the anion side. The B site transition metal is octahedrally coordinated covalently with the oxygen atoms on the outside. So, of all the elements that we can choose, we have to decide which ones to focus on. And based on decades of research, we've selected in this work to study these particular elements, both for their technological relevance as well as for their use in studying model systems. So, for reference, recall that this is the alkaline earth. These are alkaline earth elements. These are going to be found on the A side, and this is a lanthanide. So these are elements we're going to primarily focus on the A side. These iron and cobalt are going to be on the B side. Okay? And of course, oxygen is the anion of choice. So let's take some of these elements and put them into the actual structure. Here we have lanthanum ferrite. And we have 6 positive charges on the A side and 6 negative charges on the B side. So we now have charge neutrality. Right now, this material doesn't do much for us as a catalyst. What we can do to give it functionality, we need it to conduct electrons and ions. We can introduce point defects into the material. And what we can do that is by changing the A site. So we substitute lanthanum with an alkaline earth element with a positive 2+ charge. And now we have 5 positive charges on the A side and 6 on the B side. Okay, so we aren't maintaining charge neutrality. So the material will react to change the oxidation state of the transition metal. And now we're starting to get electronic conductivity. Now at the same time, you change the A side, you can change the B side. You can add more different cations. And cobalt, what it actually does is create more electronic conductivity. But it also changes the overall charge of the material. And so it must continue to compensate. And what it does is it creates oxygen vacancies. So now oxygen is missing in parts of the lattice. And what this gives the material is ionic conductivity. So now oxygen can oxidate the material at the same time that you're getting electronic conductivity. So now let's kind of zoom in to what the reaction looks like at the surface of the material. This is the side view of that unit cell as a kind of a single crystal. And so for the reaction to occur, we must have oxygen gas present. We must have electrons present, and these come from the local material. And then we also have oxygen vacancy, so the oxygen can jump into the material surface itself. And then finally, when it's all said and done, oxygen is now incorporated into the material. So this looks like oxygen absorbs to the surface. The electrons must break the double bond of oxygen and then absorb onto the surface. And then oxygen vacancies must travel and be present so that the oxygen atoms can jump into the surface of the material there. So this is kind of an idealized schematic. In reality, the cathode looks like this on top of the electrolyte. It's very porous. And it's very porous because it needs to have a high surface area so that it can have lots of reactions so it can get as much oxygen in as fast as possible. It's also relatively thick. This is about 20 microns thick. And it does this because it needs to conduct electrons in this direction, and it needs to conduct ions in this direction down to the electrolyte. And that helps with electronic conductivity. So then, let's get into the requirements of what this material system must do to function in a fuel cell. It's quite a few. It must be a good catalyst. It must be stable under operating conditions. It must have good ionic and electronic conductivity. And it must also be compatible with the electrolyte. That's a lot. So let's take a look at the ionic and electronic conductivity a little bit so you can see, okay, changing the elements around what does this do. So for the material system shown here, we have lanthanum and strontium. Strontium is the alkaline earth element. And then we change the B side from something that has only iron, and we start adding cobalt into it until it's 100% cobalt. And what we see in this graph with conductivity as a function of cobalt content, we see that both of them increase, the ionic and electronic conductivity. So this basically says that cobalt-containing catalysts are pretty good. But they're good in a lot of these areas, but they're a little bit unstable, and I'm going to talk to you about why that is. So now that we have all these material requirements, how do we evaluate if we have a good catalyst? So this is our figure of merit. This is how we're going to measure how good of a catalyst it is and how quickly it degrades. On the y-axis, we have the degradation rate as a percentage per hour of how quickly it degrades. And on the x-axis, we have something called area-specific resistance, which tells you how good of a catalyst it is. So with a very low resistance, the catalyst is very active. With a high resistance, it is less active. Similarly, when you have a high degradation rate, it's unstable, and a low degradation rate, it's stable. So our best catalysts are going to be down in this region right here. So this brings me to the overview of the entire talk. I'm going to break it up into 3 sections. First, I'm going to talk to you about how all these point defects can be put into the material that give it functionality. How do they work? Not just in the bulk, but more importantly at the surface. That's the front line of electrocatalytic activity, and we need to understand what's going on there so we can figure out how to improve any type of degradation. And then, based on what we've identified at the surface, we then figure out if we can link what the surfaces look like to their catalytic activity and stability. And finally, what we learned from these 2 sections, I'm then going to propose a technique to stabilize the surface to be stable and active under operating conditions. And to do this, I'm going to use certain types of methodology. And what I mentioned is that a lot of people study these films in a porous orientation, but these inherently convolute results because they are also high surface area. They have multiple surfaces that are exposed, and some people have issues like cracking and whatnot. So what we are studying right now is a thin film model system. We have well-defined orientations. We only have to study one surface. So that's what I'm going to reference going forward. And so once we study these systems and what we find on the surface, we then want to test them in a very precise electrochemical setup that we build ourselves. It's very clean, so that we can deconvolute any type of things that might try to confuse us in our results. Then we use, to analyze our thin films, we use things like high-resolution chemical mapping. And this allows us to zoom in and perceive what is found at the surface, both structurally and chemically speaking. So what is that at the top few nanometers of the surface? And then finally, these measurements are done ex situ. We're then going to try to see what the surfaces look like and compare them ex situ to what the surfaces look like under relevant operating conditions using synchrotron radiation and in situ spectroscopy. So first up, I'm going to focus on the bulk of the material. So I've already mentioned to you this lanthanum cobalt iron series where we add cobalt into the material system. Shown here with just 100% iron on the B side, the surface looks relatively flat. This is an AF micrograph. If you start to add cobalt, you see the surface begins to roughen, showing that there's something going on as you add cobalt. And the trend continues when you go into 100% cobalt, where you get these large islands and large bumps forming. So what we're going to use now is a technique where we can basically slice these surfaces in half and look at them from the side. And we use scattering transmission electron microscopy for that. So here, we just focus on the end members, the one with only iron and the one with only cobalt. Okay? And we can see that we have one of those bumps there on the right. We can do chemical mapping using what we call stem fields and focus in on one specific region to see, okay, where the cation is located in these areas. So we look at lanthanum initially on both of them. We see that it's relatively uniform for the iron species. But if we look at the other side on the right, we see that there's a deficient area within this large bump for lanthanum. If we compare that to strontium, we see a similar thing for the iron and the deficiency of the strontium on the right side. And now, what's illuminating is when we look at the transition metals, the iron and cobalt. The cobalt side shows us that there is an enrichment of cobalt over in these large bumps. And now cobalt, when you put it into the material, likes to create a lot of oxygen vacancies. And the oxygen vacancies can order. And so essentially what we're seeing here is that we're seeing a demixing of the perovskite into the cobalt-rich phase and the perovskite itself. So this basically tells us that things that contain a lot of cobalt are inherently unstable, particularly the bulk. So you can imagine the surface being a little bit even more chaotic. So to study the surface, what we want to do is focus in on one specific, very well-defined surface. And so we do is we study the one without any cobalt in it. So this is going to be really important going forward. A lot of what I'm going to talk about next, the material system on the B side only contains iron, okay? And then we're going to play around with the A side, where the lanthanum and strontium are a lot more. The B side is always iron. We're going to modulate the A side. So now that I've talked about the bulk a little bit, I'm now going to focus in on what the cations are doing on the surface. So I mentioned to you that oxygen can conduct through these materials. What I haven't mentioned is that cations, when they're heated up, can also start to move around. So it's not just one atom that's moving around, it's everything. Okay. So the surface can look like this. We have this thing called segregation, where the cations can move from the bulk of the material, essentially this infinite reservoir, and come to the surface. Now let's see why that might happen. So here I have the chemical potential of some species on the y-axis as a function of distance on the x-axis. Now the chemical potential can be thought of as a driving force for anything to happen. Okay? In the bulk, this is the standard chemical potential for an alkaline earth, AE standing for alkaline earth. It's relatively flat, meaning there's no driving force for anything to really move around too much. And that's represented by this distribution on the bottom of the atoms. Now as we move out to the surface is fundamentally different from the bulk. because it's essentially a two-dimensional defect where you don't have atoms crowding in and pushing everything together to hold it in place. And so the surface is a place where things can kind of expand out. And the chemical potential here essentially is a gradient to reflect that. This gradient down here means the driving force for things to drop down and become in a more favorable energy environment. So what we see, the distribution actually changes to something like this. The cations move from the bulk to this surface, essentially accumulating at the surface. And if they accumulate in a high enough limit, you reach a solubility limit where you can precipitate new phases. So this is related to temperature because the entropic contribution to the chemical potential has a temperature dependence, such that when you raise the temperature, the entropy actually pulls these atoms back in, which is kind of contradictory to what you might think. This is because of configurational entropy, for those familiar with it. Basically pulls them back in from the surface. But when you decrease the temperature, which is what people are trying to do to lower costs, segregation increases. The atoms might move a little bit slower to get out there, but you normally have entropy helping to pull the elements back in from the surface. So this leads to segregation and then precipitation of secondary phases. Now, if that were the only thing that was happening, that would be kind of nice. But at the same time that you have accumulation of atoms at the surface, you can also have them create a new termination on the surface. And then, additionally, you add precipitation, you have three different things occurring at the same time. So let's try to make sense of what might be going on with all of these within this system. So to kind of summarize what I've said so far, we have this kind of pristine surface, but in reality, you have things like segregation and precipitation occurring. Now, precipitation is considered to be a bad thing amongst in this area of research, where these precipitates, these islands, are thought to be catalytically inactive and blocking, so that you essentially passivate the surface so that it can't react so much with the oxygen gas. Further, under real conditions, as opposed to ones where you have a very controlled gas, in the air that we breathe, we have carbon dioxide and sulfur dioxides. Now these can react further with the precipitates, further passivating the surface and essentially kind of killing the catalytic activity of the material. So the motivation for the study I'm about to tell you is to try to understand what can we do to understand this process that's going on here. And so what we do is we focus on the A site. Remember, it's not the transitional. This is just the A site where the lanthanum is. And what we're going to do is we're going to distort the lattice by putting in alkaline earth elements of different sizes. We're going to expand the lattice and see what effect that has on segregation and precipitation. So what we see here is the ionic difference between the lanthanum and the calcium. The size of it is about 2% smaller. And then when you go up to barium, that's 18% larger than that of lanthanum. So you can imagine the barium doesn't fit so well maybe in the lattice. So let's see what effect that will have. Now, in addition to changing the A site size, what people have done to try to reduce precipitation, which isn't considered to be bad, is to just put less of the A site in the material, making it A site efficient, in hopes that it doesn't precipitate as much on the surface. So at the same time that we're studying A site efficiency, we're also going to study the A site excess to see, is there really a good reason not to put a lot of A site into the material? So we have changing the ionic size in the A site and putting less of it and more of the A site into the material. So for reference, for all these atoms that I'm showing you right now, I know there's a lot. For the barium substitution into the lanthanum barium iron oxide, we're going to call that LBF. For strontium, LSF, and for calcium, LCF. So let's take a look at these surfaces to see if we can already see some trends. So here's the barium sample. We have A site efficient on the bottom, moving up to A site excess on the top. And what you can see very distinctly is that you get these precipitates forming as you try to put more of A site in there, which kind of makes sense. Barium is large, and we put more of it in there than the lattice can handle. And so it's precipitating new phases on top. We move on to strontium, which has a smaller ionic radius. We don't see quite as similar of a trend. We see kind of a few precipitates forming, but we don't see anything as dramatic as the barium, and this might be due to the fact that the ionic mismatch is much smaller. When we move on to the calcium sample, however, it was kind of confusing because it has the most similar ionic radius to lanthanum, and we see this kind of rough surface morphology. I'm going to get back to that a little bit later, but first let's focus on the strontium series here, particularly A-site deficient and A-site excess. So more A-site or less A-site in there. Now, we're going to focus in and try to understand what's happening on the top atomic layers of the sample. To do that, we need a very well-defined model system. And what we do is we use atomically flat substrates to put our films on top of. This is what they look like. These are atomically flat lanthanum strontium iron oxide on top of strontium titanate, which is a single crystal perovskite as well. And they grow up ataxia. If you look at it from the side view, you can see each one of these steps is 1 unit cell in height. Just 1 unit cell. That's like 0.4 in nanometers. Now, we use high-resolution transmission electron microscopy to zoom into the surface to see if we can see any structural changes here. That's what it looks like. On the one with less of the A side, we can see a very distinct difference from the other side on the A side excess. And I'm going to highlight that right here. You can see kind of the formation of a cation double layer. Now, we see something structurally different. But what it chemically is found at the surface. To do that, we turn to the same measurement we did with the previously, where we do line scans going from the bulk to the surface, trying to do chemical mapping. And so here we have essentially those two images turned on their side, right? We have the substrate here, which is STO. We have our material of interest here, and we have the surface terminating on both sides. Okay? Now, the first graph I'm going to show you is basically the amount of A site relative to the amount of B site. And if they're equal, they're going to fall on this line here, 1. So as we move from the bulk, which is relatively constant, out of the surface, you can see that there's a big drop right here, right at that cation double layer. And what that tells us is that it's going to 0. That means that the termination layer is mostly B site, iron. When we compare this, the A to B site ratio, to that of the other sample, we see that it's relatively uniform in the bulk. But then it jumps up at the termination layer, which is very, very, very different. So that is A site terminated. Now, if we focus in on just the A site, nothing to do with iron, just the A site, when we look at how much strontium is in there, we see that it's relatively constant in the bulk, but it deviates here, right at that cation double layer, showing us that there's some segregation present. And then when we move out to the other sample, we see that we also see a similar trend right here. Now, to kind of summarize this graph, there's a lot going on, is we see a B site termination on the A site deficient layer. And then we see on the A site excess, we see an A site termination. So for the material that has the same atoms inside of it, we can get 2 different terminations depending on how much of one site we put in versus another. Now, this is interesting and all, right here. But this is also done ex situ. This is done not under relevant operating conditions, where we're actually having reactions happening in real time. So what we want to do now, as I mentioned previously, is just try to see what these surfaces are doing as reactions are occurring at elevated temperature with gas oxygen present. To do that, we go to a synchrotron source. And we do this thing, essentially, we say going to the beamline. And for a general audience of friends, family, and colleagues, not everybody knows what this is. So I'm going to explain it to you all the same way that I explained it to my grandmother. In a poem entitled How Explain the Beamed Grandma, who likes to stay behind the times with hats, gloves, handkerchiefs, and runs. Electron packets forced to circle, spinning in their morbid orbits, nipping at the speed of light, dying with the glory bright. We sacrifice them to our cause and use the radiance from their death to probe the surface of our samples, which humans were not designed to see, but we insist this not be. We ride the beamline dusk and dawn, night's questing but precariously perch, on the speed, unstable still. They beam the width of human hair, of X-ray beam. And so, what that very insight is, and what this actually looks like as a schematic, is we have these really bright X-rays really brilliant amounts of light, hitting the surface of our sample, giving us very surface-sensitive chemical mapping. And we're able to do this in a heated environment and with oxygen present. And so what I'm going to show you, I'm going to talk about what is called X-ray photoelectron spectroscopy, XPS. And what one of those spectra looks like, say for the strontium, for example, is shown here. We have the intensity of the signal in counts per second as a function of the binding energy. Now, one chemical species typically gives two signature doublets, gives us a doublet, so two peaks right here. So, to summarize, one type of chemical species environment, say that strontium atom is in, gives one set of doublets. Another one gives a second set of doublets. And the higher binding energy means that this particular species is in a high oxidizing environment. Okay? So to figure out physically where these elements are, we have to do depth profiling. Something that's more surface sensitive, something that's a little bit more bulk. And so that's what I've shown here. Again, we have the intensity on the y-axis as a function of binding energy. And on top, I have a more surface sensitive measurement compared to that below, 0.5 nanometers versus 1.3 nanometers. And if you look at the relative ratio of these two peaks, the green and the blue, you can see that the ratio changes as you go from more surface sensitive to more bulk light. And this basically tells us that the peak on the left is more found at the surface. Now, if we go to the strontium sample, we see a similar trend. The green relative to the blue decreases as you go deeper into the bulk. And so we also have a species found at the surface. Now what surprised us, well, yeah, and you can't actually see anything here. So I'll get back to this in a little bit, was what is that secondary species? But when we moved on to the calcium, what surprised us was that we didn't see anything in terms of a secondary phase, or secondary species. As you can see here, from surface sensitive to bulk sensitive, you see that the spectrum doesn't change much. So this says that calcium is found all in one environment. And that was confusing for us for a little while, because recall that what we saw with the surface, it's kind of bumpy. But what we realized is that that's more of a result of how we deposited the film. That's just how the film grew. And so right now, what we're going to do is kind of try to make sense of these spectra. How can we make physical sense of these spectra? Because right now they're just a bunch of wiggly lines, right? So one technique that we used was comparing the ratios to each other. This is a graph of the surface alkaline earth ratio to iron ratio. So these are the kind of on the A side and the B side, as a function of the bulk composition of the material. Now, if the surface looked exactly like the bulk, whatever we plot on here is going to be along this line right here, this dashed line. When we compare the ratios to each other, we get this significant deviation. Now remember with that picture that I showed you earlier with the electron microscopy, we saw something change at the surface too. Now if we take into account the lanthanum, the strontium, and the iron spectra, we can actually reconstruct what these surfaces look like. And this is what we came up with. For the A side excess, we see that we have an A side enrichment just like we did in the spectroscopy, the microscopy. And on the A side fission, we also see a B side termination, just like we did in the microscopy results. Now further, we can actually resolve what we saw earlier for the side peak. And essentially that side peak signature are these atoms, kind of just like a monolayer or so, found at the top of the surface. And so we can also extend this, not just as the strontium sample, but now we can look at the barium samples as well. And what this also tells us is that precipitation is not the best form of atomic force microscopy. Those images that I showed you at the surface are not the best way to see if something is precipitating or not. You actually see atoms on the surface, and you can't resolve them with the electron. So for the barium-containing sample, remember this is the one with the biggest ionic radius mismatch, we see a similar trend. We see that there's an A-side enrichment in the A-side excess, and we see a B-side termination on the A-side deficient sample. And just like we saw with the side peak, we have an accumulation of just barium atoms onto the surface. With the calcium, we actually see a similar trend too. You can see that it doesn't fall on this line. The surfaces does change. And there we actually see segregation, and we also see the same trend that we saw previously. we see for A site excess, we see a termination of A site cations. For the A site deficient, we see a termination of the B site cations, including the iron. Now this is interesting, but it was also a little concerning, because what was conventionally thought is that the iron is what transfers the electrons to the gas molecule to run the reaction. But, say for example here, if we don't have any iron at the surface, how does the reaction occur and take place? So for that, I now turn to the dynamics of the oxygen atoms and electrons. And for this, we turn to X-ray absorption spectroscopy, and I'm going to show you a spectra of what that is. And to actually see what a reaction is doing in real time, we're actually going to apply a bias to the sample, a voltage, to drive oxygen into the material and out. Okay? So this is what one of those spectra look like. We have the intensity on the y-axis as a function of photon energy on the x-axis. And so right here, overlaid over each other are different voltages, different biases, trying to drive the oxygen in and out to see if we're going to change the oxidation state of the iron. And if it were to change, we would see pretty significant shifts in these two peaks. But what we see right here is that not much is changing. And if we extend this to the other cations, the lanthanum or the calcium and the barium, we see that the spectra aren't changing significantly as you try to drive oxygen in and out and try to change the transition metal oxidation state. So you might have guessed already that there's something else that we haven't talked about yet, and that's the oxygen. This is the oxygen Ka absorption spectra. We have the normalized intensity on the y-axis as a function of binding energy, or sorry, not binding energy. That should be photon energy, sorry. And what we see here is that the spectra is changing pretty significantly as we try to run this reaction. And the area where they overlay is called an isospecific point. And when you have two different things changing, they create what is called an isospecific point. And so that means that there is one distinct state here and another distinct state here. Okay? And so when we look closer, we're actually talking about that these are the binding orbitals, the sigma orbital and the pi orbital for the transition metal 3D and the oxygen 2p. So when we apply an increasing anodic bias, trying to drive oxygen out of the material, we actually open up this state. And that signifies that oxygen is changing its oxidation state, meaning we're going more from 2 minus to oxygen minus, showing us that oxygen is primarily the electron transfer species for gaseous oxygen as opposed to the transition metal. Okay? Now, for those of you familiar with crystal field theory, this is the EG up state and this is the TGG down state. And so what we're doing here is we're changing, or we're basically filling and unfilling the EG up state, the high spin state. And this change here on the TGG down state is really just a change in the covalency of the transition metal oxygen bond. So to summarize what I just talked about, and we've basically seen that as we change the bulk composition of the material system, we can change the surface termination. And we've confirmed this with X-ray microscopy and in situ spectroscopy. But now this begs the question, how active and stable are these surfaces, now that we know what's on them? So to that, we now turn to measuring the activity and the stability of these films. And recall, this is our figure of merit. We want to have a low degradation rate in a very active film. And before I plot up our surfaces right now, our materials, I'm going to tell you what this final temperature current is for the same geometry that we're currently using, a very flat thin film. So here we have data from literature at different temperatures that are color-coded right here. One of the things that is obvious is that as you increase the temperature, the stability increases. Now recall that previously I said segregation and precipitation decrease with increasing temperature, so that kind of makes sense. You no longer have these things on the surface. Now, in order to test our materials and make sure that we understand exactly what's going on at the surface, we need to essentially engineer our measurements so that we don't have any convolution from everything down below. Electronic connectivity, ionic connectivity, compatibility, and electrolyte. So these are the things we want to focus on. Activity and stability. So we've already selected electrons carefully, so this is not a problem. For ionic conductivity, if you look at the thickness of the films that we're working with, they're only about 100 or 200 nanometers thick, which is not a lot of distance for the ions to travel down to the electrolyte. So we can already say that this is not going to be a rate-limiting step in the reaction of convoluting. But what you do have to worry about is that the aspect ratio for the distance that the electrons have to travel are 10 or 100,000 times farther than those of the ions. So we need to essentially engineer a way to rule that out. And the first thing that we did was put gold mesh on top. Gold mesh in bulk gold is considered to be inactive as a catalyst. And so if we do that, we can decrease the distance that the electrons have to travel to 500 microns. And this is what it looks like in reality. But that's not good enough right now, based on our simulations. What we do to overcome this further is we bury platinum current collectors underneath the film. And when we do this, now the electrons only have to travel 30 microns. So, this is what I'm going to show you to basically map out how catalytically active these material systems are. We have the area-specific resistance, how big the catalyst is on the y-axis, as a function of temperature on the x-axis. And right now, we're just going to change the A-site cation from barium to calcium. So first, we're going to start off with the strontium. And what we see here is that the ASR at 650 is about 0.3 ohms, which is actually pretty good and much better than we expected. I'll show you why in a little bit. When we look at the calcium, we see that it overlays it pretty well, which is kind of confusing initially. And we did something different, and we tried to change the lattice size. When we went down to barium, we were surprised to see that it has the best catalytic activity. And this is confusing because we thought we had all these precipitates on the surface blocking catalytically active sites. But what you can remember is that the ionic radius also has an effect in the lattice. And essentially, you can imagine expanding the lattice out so that oxygen can hop into it much easier, lowering the kinetic barrier for the reactions to occur. So now we're going to focus in on the strontium again in the middle. And recall the measurements that we did to try to see if we put in a little bit more A-site or a little bit less A-site, what happens to the surfaces. So we have these two different surfaces, A-site excess with A-site termination, A-site deficient with B-site termination. Now here's the A-site deficient. All right, if you might remember, now it's a little bit higher than we saw previously. If you compare that to the A-site excess, we see that it's actually performing better, which surprised us. Because conventionally, people only use A-site deficient in hopes that you're not going to get these precipitates. So before I talk to you about this further, let's go ahead and put on our catalyst onto this figure of merit. Our catalyst kind of fall down in this bottom left area. And this is surprising to us because we only have iron in our samples. These measurements up here were done with only cobalt. So what this tells us is that our system is very clean, and that our platform is quite good, and that we're kind of getting more towards the intrinsic catalytic activity of these materials. And so now I return to these two surfaces. And one thing I failed to mention already is that we have these two lines on here, and these two different measurements to show that we can reproduce these measurements quite well. And so right now, let's kind of focus in on the surfaces of these two material systems, not just in a very clean environment, but in a real environment where we have trace gases such as carbon dioxide and sulfur dioxide. And so the first thing that we do is we take one of these materials each, and we test them. And we want to make sure that they're operating as we expect. We have the A-site deficient here in blue, and in red we have the A-site excess. And this is the resistance, how good of a catalyst it is, as a function of time. And so this fresh sample is in a very clean environment, relatively stable. We then expose it to air after testing in 1 week. We let it sit at room temperature to see if anything happens. And what we saw was that not much changed. So at room temperature, not much is actually happening. So then we decided to take these two samples, and we're going to heat them up in air, cool them back down, and test them again. And we see is that they both have about a similar trend. The degradation rate has, they're less catalytically active, but the A-site deficient is still performing better, or A-site deficient is still performing worse than the A-site excess. However, when we test these in open atmosphere, we see a different trend. We see that the A-site excess quickly overtakes the A-site deficient. And what this tells us is that the surface with a B site termination is inherently more stable than that of the A site termination shown here. So now we've defined the surfaces pretty well, but now we're a little bit, now that we see that these materials are inherently unstable in regular air. So this is kind of frustrating. And I recall my first quarter here at Stanford, I talked with a professor, and I told him what I was doing. And one of the first things he said was, who are you working with? I said, Bill Chu. Who's Bill Chu? And then the second thing was, oh, that's a really interesting experiment, but it will never work because of this problem right here. And so now we're talking about what we can do about this situation. Essentially taking what we've learned in the first 2 sections and trying to engineer a more active surface. So to do this, we're going to hit our material systems up against the porous structure, something that has a higher surface area. And to do that, we actually need to shift this over, the scrap over, to have an even more active surface regime, catalyst regime. And when we put our literature results of all different material systems on here that are brave enough to put their degradation rates and their catalytic activity, we see that a lot of them are operating at high temperature, and we have this outlier here, which is one of the most active catalysts. It is still somewhat unstable, but doing pretty well. And so to kind of be a little bit more competitive with these materials, we turn to a sample that has a little bit more cobalt, 20%, not a whole lot. And when we put in just 20% of cobalt into this material system, we can see here, compared to what you've already seen, that the catalyst is performing much better than what we saw previously. And so when we put that on our figure of merit, say, oh, it's a better catalyst, right? But it's also degrading. And remember, this is just a thin film geometry. This is not porous, so it doesn't have the enhancement that having a large surface area does. So we have a high active material that degrades. We need to do something about that to try to maintain that catalytic activity. Now recall, we have 2 things working against us in this graphic we showed earlier. We have lowering the temperature, increasing segregation, and basically driving these precipitates from forming. So one thing that we've tried is essentially inserting a barrier just slightly below the surface. And what we've done here is we've decoupled the infinite reservoir from the bulk that allows the cations to move to the surface and to precipitate. Okay? And what you can imagine here is that when we have something that is so finite, like a 5 nanometer ultra-thin film, that anything that segregates to the surface will destabilize the film and just really won't happen. Otherwise the material wouldn't stay in the state that it is already in. And this is what we observe. So what I call this structure is a trilayer structure. And to understand what to put as this barrier layer, it must have certain characteristics. And what we show as our barrier layer initially is cerium oxide. Now cerium oxide is a fluoride structure, and it can grow epitaxially on top of this perovskite structure. Now, one of the things that we have to test first is can it block strontium? And so to do that, we essentially first look at the surface morphology. Here we have the LCF as a fresh electrode, and then we turn to the trilayer structure. We look at the surface again. They're not too dissimilar. Now, when we put them under reaction conditions, we see that after annealing at 650 degrees Celsius, the surface changes pretty significantly from the fresh sample to the annealed sample. But when we turn to the trilayer structure, we see that the surface doesn't change much. And this tells us that there are a bunch of precipitates on the LSCF here, but the trilayer structure doesn't change at all. And then when we take this to the synchrotron to do chemical analysis of the surface under the same conditions, we see that the surface is actually about 40% enriched in strontium compared to the trilayer structure. So what we can say is that this is effectively blocking the strontium from getting to the surface. Now, we also have to have 2 other requirements for the system. We have to conduct oxygen and electrons. And so what we do to accomplish this is we must substitute the cerium oxide, just like we did in the perovskite, with different elements. Here, samarium and praseodymium. And what we see here, this is the ionic conductivity in blue, and they're fairly comparable. But when we turn to the electronic conductivity, the praseodymium outperforms the samarium by 4+ orders of magnitude. This is because the praseodymium can change oxidation state, and this aids the electronic conductivity. So, let's take a look at what the degradation looks like, actually. Here's the resistance on the y-axis, a function of time for 1 day. The LCF, without the trilogy structure, you can see that it degrades over time. Now, what's exciting is when we actually tested the trilogy structure, is it was relatively flat. We didn't really see much degradation at all. And to kind of drive this point home, we look at the surfaces in the schematic. We don't have these precipitates blocking the active layer. And down here, we essentially see that it's still relatively pristine. So, unfortunately or fortunately, the resistance decreased with time. So when we put this on this plot, we can't do that because it's a log plot, and 0 does not exist. And so what we do is we just drop it down here at the bottom. So what we have is a relatively stable and very active catalyst. So that's great. But what happens in real conditions when you have trace gases such as carbon dioxide and carbon monoxide, and sulfoxide? So let's compare the LCF in real ambient conditions. Well, as you might have guessed, it does degrade faster. Then when we put on the trilayer structure, we see that it essentially overlays that of the structure that we tested in the clean environment. And this basically shows us that the surface itself does not react very well with impurities in the atmosphere, and that when you have precipitates, you're further passivating the surface. Now, to put this area-specific resistance in context, 0.03 ohms, when you apply 100 millivolt overpotential, is about 3 amps per centimeter squared current, which is pretty good. So when we focus on the figure of merit, we see that we're among some of the best catalysts in the world, both in terms of catalytic activity and stability. And we're only using thin film system. This is not porous yet. So that begs the question, what can we do to kind of scale us up into the porous system? So we have these thin films that we have to deposit on top of our LCF. And we can do this with atomic layer deposition. This has already been shown in literature, and so essentially all we need to do is to figure out how to optimize this technique. And you might have asked yourself, well, why don't we just use this as the current collector and forget about the LCF completely? Well, we still need the electronic and ionic conductivity of the LCF. It's still orders of magnitude higher than that of the praseodymium doped cerium. So, to summarize the talk today, I've taken you on a journey where I've discussed how the bulk cations can influence what you see at the surface. And based on what we identified at the surface, we then moved to correlate the surface to catalytic activity and stability of these surfaces. Based on what we learned from how these surfaces react in a very clean environment and those in an environment where we have gases that can poison the surface, such as sulfoxide and carbon monoxide, we then figured a way to engineer the surface to be stable under relevant operating conditions. So in a sense, we've completed the material science loop. We've used fundamental science to inform the engineering of our surfaces for improved performance. Thank you for your time.
Michael will take some questions now, and then we'll give his acknowledgement after that. So are there any questions?
Maybe I missed it, but what technique do you use to deposit your films?
Yeah, I didn't mention this. Pulse lids are deposition. So it allows you to deposit the films at high temperatures, like very dense, thick films, very controllably.
When we're looking at the overtime stability of the A-site deficient versus A-site enriched films, even in the fresh samples in a clean environment, like the A-site deficient samples improving in time in the beginning. What's happening?
Yeah, that is. Let's see if I can find that. That is also something that we actively want to investigate as well. So Justin's talking about this right here, and that's over the course of many hours. So you can imagine that these films are deposited in a very low oxygen environment. So they actually have a lot of oxygen vacancies. And when you heat them up in, say, 21% oxygen air, the oxygen has to go, it actually equilibrates and comes back into the film. And so at the same time that the oxygen is coming into the film, the cations are going to react. So the cations are relatively dynamic compared to the oxygen. And so what this is basically showing you is that the surface is basically slowly moving to its thermodynamic state, but it's not happening very quickly. And then that's kind of what we understand about right now, but it's definitely something we want to investigate.
So you talked about how with this trilayer structure you're able to get much improved stability at low temperatures without sacrificing catalytic activity, which should make things cheaper, which was the point of doing this from the first slide. So how much more expensive or how much harder is it to make trilayer structures if you want to actually deploy this in the real cell?
That's a good question. That's something that we are actively trying to explore in the next year, potentially with some collaborators. And with atomic layer deposition, essentially you can, the nice thing about that technique is that you can already take existing structures and you basically just have to coat the surface. And this can be done, this is already done at the commercial level using atomic layer deposition. And so we're not sure how challenging it's going to be, but it should be that much more expensive. Just take a little bit more time. Well, we're interested in exploring it.
So the trilayer disrupts the bulk to surface transition that you observe. Do you notice any phase segregation that's occurring between the LCFS, was it, and the cerium itself?
Any phase separation? Oh, you mean
Like right under that,
yeah.
under the trilayer, right?
Yeah. So that is something that we want to investigate. We haven't done that completely yet. So if I can go back to a slide more towards the beginning here. This is LCF.
Yeah.
And that is a serum oxide on top. And so you can also see the LCF is also instantly mixed. This is cobalt in red. But what you see here at the surface is not a whole lot of intermixing currently. But what we want to do is what you say is use high resolution microscopy to see what's going on under samples that have been tested for some time.
One last question. Now we'll let Michael move to his acknowledgements.
1 second. Gotta open it up because I just assume my house will be crashed. So, first thing I want to do is thank my committee. It's come our day. These are the people that inspire us. These are the people that we follow into our PhDs. And I've taken classes from you. I've been inspired by your work in catalysis and fuel cell. And I even had you, like Matteo, come to some of my group meetings and sit down and talk with me about what is going on right now and try to make sense of it. And so these are all things that I really appreciate. And then there's also this guy right here, Will. Now, I was from a mustache at that time, and they kept calling me Super Mario, so I decided why not. And throughout the years, like, Will is younger than my older brother, and throughout the years, we've figured out, kind of what the dynamic is for kind of a PhD student and mentor and advisor. And it's been really wonderful being Will's student, because every year that I would sit on one of these defenses and I'd hear someone talk about their advisor, I'd think about, like, what is it that I want to say about Will? And that would change every year because Will is very dynamic. Like, I remember in the very beginning when I was kind of like, what is going on? He took me into his office, we sat down, we had an hour-long chat just about my feelings. And how to go about mapping out the PhD, because it seemed a little overwhelming. I mean, I'm joining a lab that doesn't exist yet, essentially, save some wonderful students that were there at the beginning with me. And Will is very open to suggestions. It's been a really true privilege to be able to be mentored, but also to have someone who's willing to listen to you and to change the way that he mentors and kind of runs his lab. He takes advice from all of his students, and that's something that's very special to us. And he cares a lot about not just how we develop as people, as scientists, but also as people, figuring out how to tackle big problems. And he's always willing to understand anything that you have going on in your personal life. And so, I really thank him for allowing me to tackle all these big problems and to learn with him. And at the same time, he really encouraged us to have fun, which is I'm going to tell you a little bit more about that in a little bit. A lot of this work would not be possible without a lot of people inside, and some that have already left the group. For the bulk material, those TEMs that you saw with those pretty two-dimensional color maps were done by Berger. And the TEMs done for the surface cations, where you saw those cation double layers were done by Central, with a lot of help from Zishran on the atomically flat substrates, and just talks about what is going on. I mean, there's so many things going on. How do we understand them? And we have Hendrik, who is the support at the beamline. Now, David is someone really special. He was our first postdoc. He was something I worked with very closely initially to help with the lab setup. I'll talk about that in a little bit. And then for the trilayer structure, we have some similar characters as we try to understand what is going on, where these cations look like at the interface. And so a lot of this work wouldn't happen without people in this group. But to raise a PhD, it takes a community. And so we've had a lot of administrative support. Sylvia, Mara, Patricia, and Fee have been, we couldn't function the way that we do, trying to order materials really quickly, or take the P card and charge it and try to get a lot of stuff pretty quickly. And they've been really understanding and supportive and really talk to us and ask us how we're doing and kind of help us slow down at times, which has just been lovely. It's been fun getting to know these people. Particularly in the time when we were building the lab up, Mark has been irreplaceable. And in fact, I think we saved breaking a glove box in half. If he hadn't been there, our first glove box would probably not be in the lab right now. So he's been wonderful. And then we've had this great support staff at all the user facilities to make this work possible. And so, as Will's mentioned, I was part of one of the first class of students. And I think this is our earliest group picture, I believe. The group has grown from there, and I'll show you in a little bit. And like I mentioned, this is kind of how David posted and I felt at the beginning. This is us on our trip. We're like trying to figure out where to go. And so this is the lab space that we worked with initially. A lot of you have not seen what this looked like. This is before the renovation. We actually had 5 or 6 different rooms, maybe 6 rooms in that giant lab space that now has 2. And then we went to work trying to do something about it. And the lab changed over time. It started to fill up. And this is what it looked like before. This is what it looked like in some of its cleanest forms that you probably won't recognize now. And here's another perspective. And that's when we started to put stuff inside. And so the people that put stuff inside started to join the group. And we did, and we spent a lot of fun times here. We went out and went sea kayaking, we went on excursions together. We had evenings where we just chat around food and drinks. We went and explored the mountains together. We went and had holiday parties with dad sweater competitions. And the group continued to grow. And it's just full of just a bunch of wonderful people that it's easy to talk to and come up and try to ask for any help at all. And I've been privileged to mentor some undergraduate students, Ruben and Hansen. And Ruben's still a student here, and Hansen has joined the PhD program. And so it's been great to see him carrying over into Stanford. And so this morning, I decided to go in and take a picture of the lab right now. And I think it's actually pretty clean, which is great. And so the lab, oh no! It just, yeah, this is what I was glad this didn't happen during my defense. It's really tired right now. Here we go. now he doesn't want to do it. 1 second. Okay, it looks like this. And so we're putting a quite a few people, about 25, into a relatively small space, and we're doing well. I think we get along well, and we're really supportive of each other. And I can't thank you all enough for helping me get to the point that I am today. And one of the important things about doing all that was the humor. We didn't have a bunch of wonderful people to share these experiences with. I don't think that's worth it. It's worth it. Now, in addition to a research team, I've also had the pleasure of being on teams outside of Stanford. Namely, I spent a couple of years on a rowing team in the Bay Area, and that taught me the importance of showing up and bringing your best in group situations that everybody's counting on you. And then when I realized that I couldn't do grad school and get for 5 AM practices consistently, I took a break, and I joined the Stanford triathlon team, and which has been a wonderful support network of people all over the Stanford community, and has really given me some great balance in my life. A 5.5-year PhD also sees a lot of different types of people, and I've been able to share this more at different times. We all kind of do our different things, but there have been some wonderful people that have been there to support throughout, and it makes it really special to see where you all go. And then there's also the special people that come in and help hang out in the evenings and do silly things together. And there's a specific subset that I don't think if they had been here, I don't know. These people, Amy, Trevor, Sasha, Justin, Nick, and Beth, those have been kind of my rocks for these 5 years. And I'm just so grateful for the chance to be your friends. There's my brother. There's my brother who, coming on age, said that he would make sure that I grew up not to be a wimp. And so I've done him proud. And as I get older, I also take his fashion statements too as a sign to match. One of the people that has inspired me my whole life is my grandmother. She's here today. This is us dressing up as Christmas as characters in a play. We're wearing pajamas down below. And she's inspired because she has infinite humor and she has curiosity about everything in the world. I don't know many people that at the age of 80 would go back to the university to study Greek so that you can translate your own version of the Odyssey and the Iliad and be completed. And so she's also my muse for poetry. Whenever I would call her and I say, Grandma, guess where I am? She's like, oh, are you writing The Bean? And I'm like, yes, I am. And then we proceed to talk about how the vacancies were doing in her apartment, and she'd ask how the vacancies were doing in my material. So always something good to talk to. And then, of course, my parents were also here today. Now, they've been an unwavering support my entire life. They've also been inspiring in helping me figure out what it is that I want to do, my next steps, and the choices that I make. They constantly are trying to make the world better, working in public health, and working for populations that are underserved. And it's something that I hope to match in my life to come as well. So thank you for everything you've done. And then there's one more person. There's this guy, which you can't really see, he's kind of a dark character right now. This is my fiancé, Jonas. And he's really helped transform my life in the middle of my PhDs when I met him. And he basically helped me reimagine what was possible, not just scientifically, but also kind of the things that I value and trying to remember all the things that are intrinsically meaningful. And what happened for him, I don't know how well this would have turned out in the end. he's been a guy that's really accompanied me on the journey up to the mountaintop. And I think that I wouldn't have reached it without him. And as we look out and figure out where it is, all these other peaks to try to tackle in the future, I'm inspired by him every day, for his insatiable curiosity and interest in learning, but also, like my parents, his desire to try to affect positive good in the world through social justice, teaching underserved populations, recent immigrants, try to bring positive change in the ways that he can. So this is something that I hope that I can do as I move forward, and I hope that everybody else is considering in this kind of political state. But before we tackle another peak, let's come down and let's kind of relax and take a look and view where we go next. So with that, thank you all. Picking you up.